Engineers have had to develop very clever algorithms and ways of trying to store information in quantum computer memory and build the memory such that it's resilient to errors. Quantum mechanics has always been the domain of the bizarre and counterintuitive, but recent discoveries are pushing the boundaries of what we thought possible. Imagine a world where atoms, the building blocks of all matter, can communicate and synchronize with one another in free space without physical contact. It sounds like science fiction, but this is the new reality unfolding before our very eyes. In today's video, we'll dive into the groundbreaking discovery of atoms synchronizing in free space, explore how it works, and uncover the implications this could have for the future of science, technology, and our understanding of the universe. The discovery starts with the concept of synchronization, a phenomenon we see in nature all the time. Think of a flock of birds moving in perfect unison or a group of fireflies lighting up simultaneously. This kind of collective behavior has fascinated scientists for centuries. However, observing such synchronization at the quantum level between individual atoms was something researchers could only theorize about until now. For years, quantum physicists have grappled with understanding how particles behave under certain conditions. Quantum entanglement, quantum superposition, and quantum coherence are terms we've heard before. They describe how particles can exhibit interconnected behaviors in ways that defy classical logic. But synchronization adds a new layer to this puzzle. It's not just about particles being connected through entanglement. It's about them harmonizing their actions, as if they're part of a grand orchestra, even when separated by empty space. To understand how scientists achieve this feat, we need to look at the technology behind the experiment. At its core, the discovery was made possible through the use of ultra-cold atoms and highly specialized lasers. When atoms are cooled to temperatures close to absolute zero, their quantum properties become more pronounced. At these temperatures, atoms slow down significantly, making their behavior easier to observe and control. This is where the magic begins. The researchers used optical tweezers, which are highly focused beams of laser light, to trap and manipulate individual atoms. By placing these atoms in free space, completely isolated from external influences, they created the ideal conditions for studying quantum interactions. Then, they introduced carefully calibrated light pulses to influence the atom's internal states. What they observed next stunned the scientific community. The atoms began to synchronize their quantum states, aligning their energy levels and oscillating in perfect harmony. It was as if these atoms, separated by small distances in free space, were talking to each other and agreeing to act as one. This synchronization occurred without any physical connection or external mediator, a phenomenon that challenges our current understanding of quantum mechanics. So how is this possible? To answer that, we need to delve deeper into the quantum world. Atoms have internal states that are governed by quantum mechanical rules. When these states are manipulated using external forces like light, they can influence one another through a process known as quantum coherence. Coherence is the property that allows quantum systems to maintain a consistent relationship between their states over time. In this case, the atoms were able to achieve coherence, leading to synchronization. But there's another layer to this story. The key to the synchronization lies in the interaction between the atoms and the photons in the laser light. Photons, the fundamental particles of light, act as messengers, carrying information between the atoms. Even though the atoms are not physically touching, they can exchange energy and information through the photons, creating a feedback loop that drives synchronization. This is an entirely new way of thinking about quantum systems. The implications of this discovery are profound. First and foremost, it provides new insights into the nature of quantum mechanics. For decades, physicists have debated whether quantum behavior is inherently random or if there are hidden patterns waiting to be uncovered. The observation of synchronization suggests that quantum systems may have an underlying order that we're only beginning to understand. This breakthrough also opens up exciting possibilities for quantum technology. Quantum computers, which rely on the principles of quantum mechanics, could benefit from this discovery. One of the biggest challenges in building quantum computers is maintaining coherence between qubits, the quantum equivalent of classical bits. Synchronizing atoms in free space could provide a new method for creating highly stable and interconnected qubits, paving the way for more powerful and efficient quantum computers. Beyond computing, this discovery could revolutionize quantum communication. Imagine a network of synchronized atoms transmitting information across vast distances without the need for physical connections. This could lead to the development of ultra-secure communication systems based on the principles of quantum cryptography. Synchronization could also play a role in quantum sensing, allowing us to build more precise instruments for measuring time, gravity, and other fundamental properties of the universe. But perhaps the most intriguing aspect of this discovery is its potential to unlock new mysteries about the universe itself. If atoms can synchronize in free space, what does this say about the nature of reality? Does it imply that the universe is fundamentally interconnected, with particles influencing one another in ways we can't yet comprehend? Makaku, a renowned physicist, has suggested that this discovery could point to deeper layers of reality, possibly even supporting theories about the multiverse or hidden dimensions. The idea of synchronization also resonates with philosophical and metaphysical questions. For centuries, thinkers have pondered whether the universe operates like a grand symphony, with all its parts harmonizing to create a coherent whole. The observation of atoms synchronizing in free space lends credence to this notion, suggesting that there may be a universal principle of order underlying the apparent chaos of quantum mechanics. As with any groundbreaking discovery, there are still many unanswered questions. For instance, what are the limits of synchronization? How far apart can atoms be and still synchronize their states? Can this phenomenon be extended to more complex systems, such as molecules or even biological structures? Scientists are eager to explore these questions, and the answers could lead to even more astonishing revelations. The road ahead is both challenging and exciting. Developing the technology to harness atomic synchronization on a practical scale will require years of research and innovation. But the potential rewards are enormous. Imagine a future where quantum synchronization enables us to build computers that are millions of times more powerful than today's supercomputers. Imagine communication systems that are completely secure and instantaneous, connecting people across the globe in real time. Imagine using synchronized atoms to probe the mysteries of black holes, dark matter, and the origins of the universe. This discovery also highlights the importance of international collaboration in science. The experiment was made possible by a team of researchers from around the world, each bringing their unique expertise to the table. It serves as a reminder that the pursuit of knowledge knows no boundaries, and that the greatest breakthroughs often come from working together. As we reflect on this quantum discovery, it's clear that we are entering a new era of scientific exploration. The synchronization of atoms in free space is not just a technical achievement. It's a glimpse into the future of quantum mechanics and a testament to the power of human curiosity. It challenges us to think bigger, to ask deeper questions, and to embrace the unknown. In conclusion, the discovery of atoms synchronizing in free space is a landmark achievement that will reshape our understanding of the quantum world. It opens up new possibilities for technology, challenges our assumptions about reality, and inspires us to keep exploring the mysteries of the universe. As scientists continue to push the boundaries of what's possible, one thing is certain: the quantum revolution has only just begun. The concept of quantum synchronization is not just a breakthrough in physics. It's a phenomenon that invites us to rethink how the universe operates on its most fundamental level. To truly grasp the magnitude of this discovery, let's dig deeper into its potential applications, the challenges it presents, and the profound questions it raises about the nature of reality. Let's start by looking at how quantum synchronization connects to a broader understanding of quantum coherence. At its core, coherence is what allows quantum systems to maintain a predictable relationship between their states over time. Without coherence, the delicate balance that defines quantum systems collapses into chaos, rendering them ineffective for practical applications like quantum computing or communication. Synchronization builds on this concept, offering a mechanism by which coherence can not only be maintained but actively amplified. By observing atoms aligning their internal quantum states in free space, scientists have stumbled upon a new method for preserving coherence over longer distances and time frames. This discovery has far-reaching consequences for quantum computing, where qubit stability has always been a critical limitation. Take quantum computers, for example. Unlike classical computers, which rely on binary bits of information, ones and zeros, quantum computers use qubits, which can exist in a superposition of states. This allows quantum computers to process vast amounts of information simultaneously, making them exponentially faster and more powerful for specific tasks. However, qubits are notoriously fragile. Any interaction with their environment can disrupt their quantum state, a phenomenon known as decoherence. Now imagine using quantum synchronization to combat decoherence. If qubits can be synchronized in free space, maintaining coherence even in the face of environmental disturbances, it would revolutionize the field of quantum computing. This would lead to machines capable of solving problems that are currently impossible, such as simulating complex chemical reactions, optimizing global supply chains, or even deciphering the mysteries of protein folding to unlock cures for diseases. But synchronization's potential doesn't stop at computing. One of the most exciting applications lies in the realm of quantum communication. Today's internet relies on classical methods of transmitting data, which are inherently vulnerable to interception and hacking. Quantum communication, on the other hand, offers unparalleled security. By encoding information in the quantum state of particles, scientists can create communication channels that are fundamentally unhackable. Any attempt to intercept the data would immediately disrupt the quantum state, alerting the sender and receiver to the intrusion. The discovery of quantum synchronization could take this a step further. Instead of relying on physical connections like fiber optic cables, synchronized atoms in free space could act as the nodes of a quantum network, transmitting information instantaneously across vast distances. This concept, often referred to as a quantum internet, could revolutionize how we share information, making global communication faster, more secure, and more efficient than ever before. And it's not just communication that stands to benefit. Synchronization could also enhance quantum sensing, a field that involves using quantum phenomena to measure physical quantities with unprecedented precision. For instance, synchronized atoms could be used to build highly accurate atomic clocks, which are essential for applications like GPS navigation, telecommunications, and scientific research. These clocks could be so precise that they lose only 1 second every billion years, enabling us to measure time and space with unparalleled accuracy. Another intriguing application lies in the study of fundamental physics. By using synchronized atoms as ultrasensitive detectors, scientists could probe the mysteries of dark matter, gravitational waves, and other phenomena that lie at the edges of our understanding. This could help answer some of the most profound questions in science. What is the true nature of dark matter? Are there hidden dimensions in the universe? And what lies beyond the observable cosmos? But as exciting as these possibilities are, they also come with significant challenges. For one, achieving synchronization at larger scales will require advances in both theory and technology. While the current experiments have demonstrated synchronization between a small number of atoms, scaling this up to more complex systems will be a daunting task. Scientists will need to develop new methods for controlling and manipulating quantum systems, as well as address the practical limitations of current technologies. Another challenge lies in understanding the fundamental principles behind synchronization. While we know that coherence and photon-mediated interactions play a role, the exact mechanisms are still not fully understood. This opens up a fascinating avenue for further research. As scientists work to unravel the deeper laws governing quantum synchronization, these insights could lead to new discoveries that reshape our understanding of the quantum world and its connection to the macroscopic universe. And then, there are the philosophical implications. The synchronization of atoms in free space raises profound questions about the nature of reality. At the quantum level, particles behave in ways that defy our classical intuitions, exhibiting properties like superposition, entanglement, and wave-particle duality. Synchronization adds another layer to this mystery. It challenges us to rethink our assumptions about how the universe operates, suggesting that even in the seeming randomness of quantum mechanics, there may be hidden patterns and principles waiting to be uncovered. This discovery invites us to consider the possibility of an underlying order in the fabric of the universe, a kind of hidden harmony that connects everything at the most fundamental level. If atoms can communicate and synchronize across free space without physical contact, it raises the profound question: is there a universal mechanism of connectivity we have yet to understand? Could this synchronization